Good day, ladies and gentlemen. My name is Cheng Binyao from Beijing University of Posts and Telecommunications. It's my great pleasure to share our recent research work on a beam tracking scheme based on deep reinforcement learning for multiple vehicles. The content of this presentation is divided into 4 parts. In section 1, I will firstly introduce the background and present our contribution in this paper. In the second part, I will propose the system model of the beam tracking scheme for multiple vehicles. In the next section, our problem will be formulated, and then we will adopt a deep reinforcement learning scheme to solve the problem, which can jointly select beams for multiple vehicles according to their predicted positions. Furthermore, the simulation will be shown in the 4th section, and I will make a conclusion in the final part. As we all know, in the next generation mobile communication, the Internet of Vehicles is one important application scenario. In order to ensure ultra-reliable and low-latency communications, millimeter wave and massive MIMO are adopted. The large beamwidth of the millimeter wave can provide a high transmission rate, and the massive MIMO provide a high transmission gain. However, when the beamwidth generated by massive MIMO is fixed, because the base station selects beams for vehicle periodically, the high vehicle speed makes it difficult to guarantee the accuracy coverage, and the narrow vehicle spacing can cause high inter-vehicle interference. Therefore, choose the proper beam direction according to the trajectory of vehicles, which is known as beam tracking technology, can balance the contradiction between interference and coverage. In our paper, we propose a position prediction and joint selection scheme to select beams for millimeter wave and massive MIMO served multiple vehicles. In order to improve the beam coverage, we employ LSTM to predict the future vehicle trajectory. Meanwhile, the MLP network is adopted to divide vehicles into clusters for reducing the complexity of the scheme. Furthermore, we use deep Q-learning network for seeking the optimal beam directions, and the objective in each cluster is further decomposed for the low complexity. It can be easily noticed that our scheme achieves better transmission quality than other compared schemes through the simulation results. In addition, we also prove the superiority of the scheme and the different setups of moving condition. In this section, we will introduce our system model. As shown in the first figure, there are k single-antenna vehicles driving on the single-lane road, and the base station is located away from the middle of the road, equipped with NBS-ULA antennas. The frame structure is shown in the second figure. A beam selection period consists of I uplinks intervals and J downlink intervals. The vehicles could periodically report their locations to the base station by uplink, and the base station intelligently selects the beams for the downlink data transmission. We assume that the channels from the base station to the vehicles satisfy the standard LOSP path loss model. Therefore, the complex channel vector can be written. In order to reduce the system complexity, the discrete beams are generally adopted in system, and the signal model can also be noted. Therefore, the received signal of the case vehicle can be expressed, which include the signal of its own beam, the noise of other vehicles, the complex additive white Gaussian noise with normal distribution. Based on the above equation, we can obtain the signal-to-noise ratio and consider the received signal can be decoded successfully if it exceeds a given threshold. Therefore, the objective of this paper, to maximize the successful transmission probability, can be formulated as to maximize the average successful transmission probability in each beam selection period. In this part, we use deep reinforcement learning to formulate the beam selection problem. In order to efficiently cover the vehicles, the base station should predict the future vehicle positions according to their history trajectories. Therefore, we use the state set include not only the current position, but also the history trajectory of all the vehicles. The purpose of our scheme is to learn for an optimal set of beam directions, ensuring the high data transmission rate in each beam selection. So the action site is the beam directions, and the instant reward can be defined as the average successful transmission probability of all the vehicles. According to reinforcement learning, we combine short-term reward into long-term reward to learn the optimal strategy. Therefore, our objective can be formulated, which can be re-instructed as expression of a value function. So our strategy is to obtain the maximum objective, which is equivalent to maximize the value function. As shown in the figure, our proposed scheme consists of 3 modules, and we will elaborate on them in the next. In the trajectory prediction module, because the beam direction determined at the beginning of the selection period needs to cover the trajectory of vehicles in the whole period, we use the LSTM network to predict the future position in order to ensure a more accurate beam coverage. We use the historical trajectory of the vehicle as the input, and the network the output of the position in the next beam selection period. It's apparently known that if all the interferences are taken into account, the scheme needs to jointly select beams for all the served vehicles, which lead to overwhelming computational complexity. Therefore, in the vehicle division model, the key vehicles are decomposed into U clusters according to vehicle spacing, where the interference between any vehicles in different clusters is small and can be ignored. Specifically, the interference is only considered in each cluster. Therefore, each vehicle cluster can use the reinforcement learning model for independent learning, and the state of each model can be rewritten. Ku is the number of the vehicles in the use cluster. Hence, each cluster can respectively select their own joint beams. Moreover, the instant reward can also be decomposed into each cluster's average successful transmission probability, and we can obtain each cluster's reward. In the same way, the value function can also be decomposed into the value function of the vehicle cluster, and our strategy is to maximize the value function of each cluster separately. In beam selection module, the joint objective of each cluster is decomposed to simplify the selection complexity. The reward of the vehicle cluster is used to judge the quality of the joint action, so it can be decomposed into contribution of each action. According to the participatory of the problem, the next state of the vehicle has nothing to do with the current action, so the formulation can be decomposed into the formula forms. We can know that the optimal beam selection trajectory for each cluster is equivalent to choose the optimal beam for each vehicle, respectively. In this section, we evaluated the performance of the proposed scheme under different scenarios. First, in the left picture, we can see that the successful transmission probability gradually conversed with the increasing number of interactions, which validates the coverage of the proposed scheme. In the right picture, we give other schemes for comparison. One is the DQN scheme, in which the beams for vehicles are directly selected based on DQN network. The other is position-based beam selection schemes, in which the beams for vehicles are directly pointed to the current vehicle positions. The red picture indicates that the proposed scheme performs better than the other schemes, because both the beam coverage and interference are taken into account. In Figure A, the successful transmission probability first increases and then decreases with the increasing vehicle mean speed, because for a given number of antennas at the base station, the beam width is fixed, then the average coverage gain will drop with the increasing speed mean of vehicles. Meanwhile, the mean distance between vehicles will increase based on traffic theory, and therefore the interference will be mitigated. In the low-speed mean, the gain digression dominates the performance, while the interference mitigation dominates the performance in the high-speed mean. Figure B indicates that in the successful transmission probability becomes worse with the increasing speed variations. This is because some inter-vehicle distance decrease with the increasing speed variance, which results in interference among vehicles. Although other inter-vehicle distance become large, the contribution of the decreasing interference is tiny. Figure C also shows a decreasing tendency in successful transmission probability with the increasing vehicle distance variance, which could be explained by the same reason for Figure B. The left figure illustrates the successful transmission probability versus the number of antennas at BS under different moving speed setups. Based on the antenna theory, the beam width decreases with the increasing number of antennas. The wide beam could achieve better coverage with high interference, while the narrow beam has low interference with limited coverage region. During a beam selection period, the coverage and beam gain should match the moving speed and the inter-vehicle distance. Therefore, the performance first increases and then decreases with the increasing number of antennas. The right figure indicates that the relationship between the successful transmission probability and the size of beam direction sites under different moving speed scenarios. With the increasing number of candidate beams in the beam direction site, the transmission performance gradually becomes better, because the beam direction site with the increasing number of decreased beams could gradually approximate to the continuous beam. Then the optimal beam selection could be realized at the cost of slight complexity increase. In the last section, we will make a brief summary of our work. We consider a scenario that an IOV system with mmWave and massive MIMO serves multiple mobile vehicles by periodically beam selection. In order to improve the transmission performance, influenced by both beam coverage and interference on our considered scenario, an intelligent scheme is proposed. The scheme first predicts the future trajectory of vehicles, and then selects beams with low complexity by dividing the vehicles into decoupled clusters and decomposing the clusters around the objective. Simulation results indicate that the proposed scheme performs better than any other schemes through balancing the beam coverage and interference. Moreover, the effects of traffic pyramids could provide a reference for periodical systems. The above is my report. Thank you for your patience.